Michigan State University, and who is online. Next, we will have the second reviewer, Gordon Blair, who is professor at Lancaster University. Next, we will have the members of the jury. I will start by the remote people. So I will start with Serge Stinkwich, who is associate professor at the University of Macau. Then we will have Anne-Cécile Orgerie, who is CR at Université Rennes 1, here at IRISA. Next, I think I will have a set of questions, and then Benoît Combemal, professor at Rennes 1, also here, member of the jury, and then the supervisor of this thesis. I will start with Jean-Rénal Dedrosy, who is DR CNRS at, I forgot the name.
University of Rennes.
This University of Rennes, okay, that's easier for me, thank you. And the director of the thesis, Johan Boursier. Okay, so June, you will have 45 minutes for your presentation, and we will start the question right after that, if you're ready.
Okay, I'm just removing that. Okay, thanks. Okay, so let's go.
Yep.
Hi, my name is June Sallou, and I will present here today the work of my PhD, which deals with the approximation of scientific software to support decision-making in environmental science. First, I want to thank everyone who is attending my presentation, either physically or remotely. And, well, I will present the different work I've done during my doctorate, which took place at the University of Rennes 1 and was a collaboration between two labs, IRISA, specialized in software engineering, and OSUR, Géosciences de Rennes, specialized in environmental science. During that time, I received the advice of my three supervisors, Johan Boursier, Jean-Rénal Dedrosy, and Benoît Combemal. Of course, I forgot, but, well, I want to thank especially the different members of the jury that are attending my presentation. So now, let's dive into the subject and start with a little bit of context. Climate change is affecting our everyday life, and according to the Intergovernmental Panel on Climate Change, it will do so even more in the future. Climate change can manifest itself in several ways and has different consequences. For instance, it can lead to the rise of the sea level, as well as the rise of the level of the underground water, leading to flooding events and impacting the land use. That's why people making decisions about the land use need to take those events and related risks into account. Let's take the example of Adélie. Adélie is the mayor of Saint-Malo, a coastal city in Brittany, France, and she is a policy maker. She makes decisions about the land use of a city. One day, Matthew comes to see her and asks her about a building permit. He is a realtor and wants to build a camping site in a particular area of Saint-Malo, which is just in front of the sea. However, Adélie doesn't have much information about the risk of flooding there, and she doesn't know how to answer. At the same time, Alexandre, who is a scientist and expert in hydrology, is building some scientific models and software to simulate the movement of the underground water of different particular areas of the real world. And they use those software to predict different risks, and especially flooding. Well, using that type of software would be a great help to Adélie for her to have some information about the risk of flooding and to be able to answer the request of the building permit by Matthew. But well, using those scientific software in that context would require a few things. First, because we are dealing with climate change and the future, we don't know what will happen for sure. So scientists have elaborated different scenarios, climate scenarios, from the most pessimistic one to the most optimistic one, in order to cover all the possible outcomes. So scientific software need to be able to provide that exploration of the climate scenarios. The second requirement deals with the reliability of projection. Decision makers will use the simulation results to make their decision about the land use, so they need to be able to rely on those results. Here I'm just taking a moment to clarify or to specify the fact that I'm using the definition of reliability to express the fact that the decision makers need to be able to rely on those results. I'm not using the commonly used definition that is used in software engineering and dealing with the fact that software may have the property of being failure-free. Okay, so the third requirement, which is interactivity, decision makers need to be able to explore the different climate scenarios, but they may come up with, for example, different solutions they want to explore. For example, modification in the land use, and they want to see the impact of those modifications on the different flooding risks, for example. And lastly, we have the generalization requirement. Decision makers, for example, Adelie, wants to have information about the particular area that Matthew is interested in, but she also wants to have information about different parts of a city for later requests. So those scientific software need to be able to explore different climate scenarios, but also different localization. Okay, but well, those scientific software at the moment, they can't really fulfill those requirements because they are too long to execute. The time is too long to produce and obtain the different simulation results. So well, to answer that problem, we need to ask ourselves how to tailor the scientific software to support decision making. In other words, how to make their execution time faster. And well, because we want an approach that is not really specific for one model and one case, we want to build and elaborate a systematic approach that will be used for several scientific models and several scenarios and cases. And well, because we are also dealing with decision makers and decision making, we want to have an approach that is easy to set up. So we have discussed a little bit about the context, and we've seen what the problem we want to tackle. Now, and in the following moments of the presentation, we will talk a little bit about the background. We will discuss the different approaches that can be used to tackle the problem. We will discuss the different contribution of this PhD, and then finally we will conclude and talk about the perspective of the work that was done during that PhD. Okay, so just a little bit of background to have some common knowledge about what scientific software entails. Scientific software are pieces of codes that are used to study and simulate different phenomena happening in the real world. And they are used to study those phenomena thanks to their computational execution that we call simulation. The elaboration of scientific software is linked to different artifacts. First, from the observation of the behavior of the physical phenomena happening in the real world, we want to build the first model. That first model is a mathematical model, and it corresponds to continuous mathematical equation. Because the end goal is to study those phenomena happening in the real world thanks to computers, we need to discretize those continuous mathematical equations. That's the role of the numerical scheme. It's a discretized version of the continuous equation of the mathematical model. Once we have that numerical scheme, we can implement it into the scientific software, which are really the piece of code that will compute and execute the equation to have the information and the behavior of those events. I just want to specify that we are here focusing on scientific software that are dealing with mathematical and numerical models, and with simulation, which are different iterations which are successive and that are used to compute for every iteration the same equation. Okay, so now that we know what scientific software entails, we need to look, and we want to look at the different and possible solutions to tackle our problem or making the execution time faster. To do so, I will present 4 main approaches, and I will discuss how they fit in our context of decision making. The first one, the high performance computing approach, deals with the fact that instead of running the simulation on a single computer, it will run the simulation on a high number of computers. However, that approach requires access to a large amount of high-performance computational resources, and it may not be easy to set up. The second approach, the model reduction approach, stems from the idea that the long execution of the simulation is caused by the complexity of the mathematical equation. So they aim to simplify those mathematical equations to reduce the execution time. However, it requires a lot of expertise of the domain and is time-consuming. The third approach, the data-driven approach, has a goal to build an analytical model to predict the outputs of the simulation thanks to its inputs without running the simulation thanks to data of previously run simulation. But well, it requires a lot of data, so to run a lot of simulation. So not really easy to set up either. And the last approach, approximate computing, which is basically a software engineering approach and is composed of 2 steps. The first step is skipping the computation of some iteration of the simulation and then interpolating the results of those non-computed iterations. However, the interpolation operator is domain specific, and one for environmental science doesn't really exist yet. For instance, for a model that simulates the underground water movement for an iteration, that iteration will compute the depth or the level of the underground water thanks to the previous computed level of the underground water. So skipping the previous iteration will make the simulation different because the data won't be processed. The data won't be the same during the processing step. So well, approximate computing is easy to set up and can be used to fulfill our requirements, but it needs to be a little bit more adapted to our scientific software. And to do so, we are faced with 3 challenges. The first one, we need to understand how scientific software are a little bit different or special compared to other type of software. Then we want to adapt approximate computing to scientific software. And lastly, we want to create the best trade-off that is applied during approximate computing between accuracy and time execution. Okay, and to do so, well, we will employ a method that is composed of 4 different steps. The first one, trying to understand the difference or the similarities between scientific and engineering models. The second one, about what really is special about scientific models and especially in the validation process. The third one is, well, adapting approximate computing to scientific software. And lastly, predict the best trade-off that can be made when applying that approach. So let's move on to the contribution. Here we want to apply approximate computing to scientific software. And well, so software engineering, approximate computing is a software engineering approach. So we want to understand how scientific models are used in relation to engineering models and also how they interact together and with data. And that's what the first contribution that is called the MODA framework, Model and Data Framework, can answer. We take a look at scientific models and how they can be used and also the different roles they can take and their interaction with data. The different roles that the scientific models can have or can play is, the first one is a descriptive role, a predictive role, or a prescriptive role. And well, what we can extract from that formalization, that framework, is, in our case, we want the scientific software, which has a descriptive role, to take a predictive role, to predict, for example, the risk of flooding in an environment, in a prescriptive environment, because decision makers will enact the land use decision thanks to those prediction of the flooding risks. So, well, that a contribution is an international collaboration between many researchers specialized in software engineering, and it allowed us to understand how to correctly apply software engineering practices according to the role that the scientific software plays. And that contribution resulted in a publication in the software magazine. Now that we understand what the approach will entail and the different roles that the scientific software will take, we need to check and to understand how to ensure that our applying the fact that we apply our approximate technique will produce some results that are still reliable. And that's the goal of the second contribution, that is called the scientific V model. Here we take a look of the elaboration of the scientific software, but really we also deal with the different roles that stakeholders that are involved in that elaboration and where they can act during that elaboration. But the focus is really on the validation of the scientific software, meaning that, well, scientific software are software, so we need to verify and validate those software thanks to software engineering concerns. But because it's also a scientific software, we also need to validate the scientific part of the software according to the different artifacts that are encompassed into the scientific software. So, well, what we can take from that contribution is that when we will apply approximate computing to scientific software, we also need to validate that application thanks to domain knowledge. This contribution resulted also in a publication in the computer magazine. Now that we know what the application of approximate computing will entail, and that we need to validate that application thanks to domain knowledge, we can apply the technique. So, well, here you have the representation of a simulation model. We take the example of an hydrogeological model. So that takes into for our inputs data, some data about the land use, the weather, and geology, and then process those data to produce some simulation results. For example, the localization and the movement of the underground water. Okay, so that's a representation, but taking a software engineering point of view, we can represent that software and that simulation model as a for loop that does some iteration, and for each iteration computes the calculation and process the data to produce the output. However, that's the representation for the scientific software that is taking too long to produce results. So we want to apply approximate computing on that software. What we do here is, well, first we want to skip the computation of some of the iteration. So instead of computing all the different iterations, we want to only compute one out of the number p iteration. That's why in the loop declaration we put p as the value of the step. Then, well, after the computation, we want to interpolate the different results of the non-computed iteration. That's what we do thanks to the function that is called interpolate. Well, now if that's okay, we have applied approximate computing, but we need to tackle the issue that we've discussed at the beginning of the presentation. We want to make sure that all the different data are taken into account to have similar simulation. And we do that thanks to another added step linked to the interpolation that we call the aggregation part, and is represented by the aggregate function here. So what it does is aggregate all the different values of the non-computed iteration into one aggregated value for the computed iteration. That way, all the different values, input values, are taken into account when there's a processing step. Okay, so that's how we apply approximate computing. Just here to sum up a little bit about the organization, about the approach. We have the scientific software, which is taking really a long time to process and to produce the data. We transform it, we apply the loop aggregation, which is the approximate computing technique for scientific models, and we produce an approximated version of the model, which is really faster. And here you can see that there's two different types of way or to implement that approach. The first one that we have already described is the fact that we have all the different steps of aggregation, processing, and interpolation done at the same time. It's a white box implementation because you need to modify the piece of code that deals with the processing at the same time. Well, we need to modify the code, so we need to have access to the code. And that type of implementation corresponds to context when we don't have data at the beginning or before doing the simulation. So when data are coming through along over time. Another type of implementation is more a black box implementation when we have all the different data at the beginning of running the simulation, so we can perform the different steps and different phases, aggregation, processing, and interpolation at different time and optimize their execution. Okay, thanks to that organization and the fact that we added that interpolation aggregator operator of aggregation in that way, we have an approach that is flexible and can be used in different contexts. Now, just to represent what we did for the model we use as an example, which is an hydrogeological model. Here is the aggregation step. On the left, you can see the data, initial data, that is used by the model. Each row corresponds to an iteration. And what we want to do is, well, skip the computation of some iteration. Here, 1 out of 2. That's why the aggregation parameter is equal to 2. And what we do, we skip those iteration, those lines, those rows, and we aggregate the values of those non-computed iteration into an aggregated value for the computed iteration. Here we use the mean to aggregate those values. In a similar way, here we have the interpolation, an example of how we do the interpolation. First, we have here the results of the different computed iteration, and what we want is to interpolate the results of the non-computed iteration. What we do is we take the different values of the computed iteration, and thanks to a linear regression interpolation, we obtain and compute the results, the projected results of the non-computed iteration. Okay, so now we have applied approximate computing. We've made sure that we could take into account all the different data. Now, well, we need to know how much we can aggregate and approximate our model. Really, what value to use for P, our aggregation parameter. But also we need to make sure that when applying that approach, we will produce reliable results for our approximated version of the model. So what we do is, well, we need to compare the simulation results of the initial model to the simulation results of the approximated model and validate the approximated model thanks to the domain experts and the knowledge. Well, we did that, and we did take some time to speak with domain experts and hydrologists to come up with acceptability metrics and acceptability criteria. So, well, the idea is, that is represented here, is that in the underground, we divide the underground in two different zones. Here, first, you have the first line here in black is representing the surface, and below that line is the underground. Then you have the blue line, which represents the water table, so the level of the underground water. And what we see here is that there's two different areas. A first one, just close to the surface, which correspond to a dangerous or saturated zone. And when the underground water is located in that zone, we don't want discrepancies between the value of the simulation results between the initial model and the approximated model. Because when the underground water is located in that area, it is a high risk for flooding. However, when the underground water is below that area, when it's deeper, there's a lower risk of flooding, so we can accept some discrepancies between the different values of the simulation results. Well, those concepts and information were put into different metrics that we see here. What we need to understand there is just to remember that it's that criteria, that metric, the H indicator, that will be used to define when the approximated version of the model is valid or not. If the value of that H indicator is below 0.1 meter, then the approximated version of the model is valid and produce acceptable results. So here are the results for our example of the hydrogeological model, and what we can see is that all the different simulation here corresponding to different aggregation rates, so different values of the aggregation parameter, are here, they're below that threshold of 0.1 meter. All those approximated models are acceptable, are valid, and we can see that the best trade-off and best speed-up that we can obtain is for the aggregation parameter of computing one iteration out of 365 iteration. And we can have a speed up that is around 96%, with results that remain acceptable. So well, to conclude, we did apply that approximate computing technique, we did adapt it for scientific software, and we managed to have some good results according for the speed up. We did that, we did apply that technique with several aggregation strategy and for several simulation cases. That contribution resulted in the publication for a conference, the International Conference on Computational Science. Well, now we have elaborated, we have applied our approximate computing technique on a specific model, but we need to remember that our simulation model will be used to explore different scenarios, different sites. So, well, we need to apply that technique for new scenarios. And some questions that we need to ask are, okay, so for a new scenario, what is the value of my aggregation parameter that I need to set? And how can I ensure that the produced results are still reliable? And all of that without running the simulation. What we do to answer those questions is, well, we use a predictive model. That predictive model will predict the value of our H indicator, which defines if the value of the aggregation parameter is correct to produce simulation results that are acceptable. To produce or to elaborate that prediction model, we have an elaboration process that is involving a learning algorithm that needs to have some data to build that predictive model. The different data that we need are the different values of the aggregation parameters, the different cases, for example, climate scenarios or localization sites, and then also the features. The features are information to discriminate between the cases, because we want the predictive model to predict the right or specific value of the H indicator to the specific cases we want to explore, the new scenario we want to explore. Okay, so what we did and the approach what we did is really adopt the commonly used pipeline, machine learning pipeline composed of 4 different stages: the data collection, the feature definition step, the elaboration of the model, and its validation. During those steps, first, what we did is we run several simulations corresponding to different cases. We collect the different value of the aggregation parameters and the corresponding value of the H indicators. Then, for the second steps, we did define some features to be able to discriminate the different cases. After that, to elaborate the different the model, the predictive model, we divide that dataset into 2 datasets. The first one is a training dataset that is used to build the predictive model, and the testing dataset that is used to evaluate the quality of the predictive model. While doing the validation of the predictive model, we use a metric here that corresponds to the percentage of error or overestimation that the predictive model is doing. Okay, so because the elaboration of the predictive model is involving different factors, we want to investigate how to build the best predictive model with the best quality of prediction by exploring how those factors can impact that quality. Well, that investigation and that exploration is really multidimensional, and a lot of different values for each factors can be used. And because it takes a lot of time and may be impossible to carry out, we reduced that dimension, that exploration, to explore different few values for each factors. What we did explore a few numbers of aggregation parameters, a few number of cases, different scales for the cases, and different type of features. Here are the different results of those exploration, and what we want to do when we want to understand and see is that the different representation and the different line on the graphs represent the error, the metric that we use, and what we can extract from that is that basically using more cases in the training dataset would lead to a better quality of the predictive model, which is quite usual when doing machine learning approach. The other information we can extract from that is that it's not really the number of features you use in your dataset, but more the quality of those features that can impact the quality of the predictive model. Because here, the different sets of features that are represented by the orange and blue lines, the different lines are quite similar every time. And, well, the difference between the two sets are the numbers of features. And they are quite similar. So that's one information and message we can take away from that. Okay, so to conclude a little bit, well, we did manage to predict, to have a better application of the approximation model, approximate computing technique, instead of applying it with always a value of 2, so approximating 1 out of 2 iteration, we have a better value for that aggregation parameter. We did a first investigation in what different factors can impact the quality of that predictive model to have the best trade-off possible. Finally, well, thanks to that approach, when applying approximate computing on new scenarios, we fulfill that requirements of exploring different scenarios. Now, I will conclude that presentation and talk a little bit about the different perspectives. Well, the problem we had to tackle is to use the different scientific software in the context of decision making, and to do that we needed to make the execution time faster. Applying our approximate computing technique that we call loop aggregation and the trade-off optimization approach allowed us to reach a speed up of the scientific software and to fulfill the different requirements that are linked to the context of decision making. In all, we did tailor the different models to support decision making. Also, I want to specify and to note that all the different approaches combine information or more knowledge from the software engineering domain with knowledge of environmental science, which is quite new in research. And combining all that knowledge allowed us to make the scientific software usable in a new context, that is decision making. And to do and apply and to tackle our issue, we did that thanks to 4 different steps and 4 different contributions. The model framework, the scientific V-model, the loop aggregation technique, and the trade-off optimization. So all that work can lead to different perspectives and further research. I will present 3 different perspectives. The first one, the generalization of my work. The second one is the use of artificial intelligence for scientific modeling globally. And lastly, about ICT for us. The first one, well, we did study and apply approximate computing on a specific hydrogeological model, but we can wonder how applying those techniques can impact or can produce different results of observation, with different types of scientific software. Also, during our trade-off optimization, we use some machine learning techniques to optimize and to have a best quality prediction model. Well, we can wonder and try to investigate a little bit further in how to make that quality of prediction even better. And a way to do so is to integrate some knowledge about the domain of the model. So, for example, here integrate some information about how the physical phenomena can happen. Because if we integrate some information about the physical processes that the simulation does, we can maybe infer easier some information about how we can aggregate and approximate those phenomena without reducing the quality or the purpose of the physical phenomena. Then we have, well, during all that trade-off optimization, we use machine learning, which is a subset of artificial intelligence. And well, okay, we did apply it to be able to explore different scenarios and to apply our software engineering approach, which is loop aggregation and approximate computing. But we can use artificial intelligence in other, more broad, in other contexts, and especially linked to the modeling step and the execution of the scientific software. Here, artificial intelligence could be used to give some recommendation to the modeler or the scientist to, for example, during the modeling stage, to have information about the exploration of the design space of the model, or do the calibration more efficiently, and so on, so that the scientists can know about when their model is valid or not. Then, well, not for modeling or building the model, but more to have information about the execution of the scientific software and how to execute it in certain ways that are adapted to the context of execution. For example, have some recommendation about the deployment strategy of a scientific software. Finally, to make some prediction, for example, about the execution time and the carbon footprint that running the simulation would lead to without even running the simulation, so that the scientists would have those information and may modify their scientific software accordingly, so that we can, for example, save energy because we won't run the simulation and produce a scientific software that is more efficient and adapted to the context. And well, all those different recommendations could be included into a development environment for scientists to have all those information directly when they are developing their scientific software. Finally, the last perspective, which deals more with ICT4S. And well, when we are considering sustainability, we want to have an holistic view and the whole complete picture to understand what are impacting different activities. For example, in our cases, we use one specific and single hydrological model to represent the movement of the underground water, and decision makers will use those information to make decision about the land use. But it's not really enough in some contexts, and we may want to have different scientific models to interact together. For example, one model about the underground water movement, but also one model to represent the phenomenon happening on the surface, and then they can also interact with what is happening underground. So we need some communication in iteration between different models, scientific models, which are really complex. So we may wonder how to apply different software engineering techniques to make those complex models interact together, but also how to use them in a context of decision making or other contexts where we need some fast decision and information. And well, all those different topics are really interesting, and well, I am interested in those two topics and passionate about bringing all the different knowledge about environmental science and software engineering to create new solutions and adapt different scientific models to specific contexts. So that's why I'm looking for a postdoc opportunity on those specific topics. Thank you for your attention, and I will gladly receive your different questions. Thanks.
Thank you very much, June, for respecting the time. We're even a little bit in advance. Perfect. So it's time to start with the question, and we will start as planned with the reviewers. And Betty, if you please want to start the question.
Okay. Thank you very much, June. That was a very nice presentation. A really good overview of your work. Exciting work, and I think all quite timely and quite relevant on a global scale. So I have a few questions, and some of them you probably already know about because we've discussed them with my written comments. And the first one I think is perhaps just a terminology issue, and it's relating to, you already addressed it to a certain extent, is the notion of reliability. And I appreciated the fact that you clarified in your presentation that you're not referring to the software engineering term about reliability and the failure of systems. But on the other hand, I guess I'm not quite convinced that you're just using a variation of the word rely to talk about the reliability of the models. So I think what I would ask you to think about is what is it that you want the users of your system and your work to think about using this term reliability. So some terms that maybe you could consider is thinking about scientific integrity, right? You want to make sure that the users of the models, the model integration, and the notion of the what-if scenario explorations is that they will trust, right, the scenario results that you are exploring, right? So to me, that is really about model trust and also trust in the data itself. And when we talk about data, we can talk about the provenance of the data, right? The completeness of the data, the integrity of the data, you know, and also even the granularity of the data, right? So all of that is, I think, all encompassed by this notion of scientific integrity, right? And so I still have an issue with using the term reliability, but I think that if you decide to use the term reliability, then I would request that you try to expand it in the terms of scientific integrity and the notion of trusting the data and the models. It's not just about relying on the data and relying on the models, because I think it's beyond that, right? And also, I think it's when we talk about reliability in the science, they usually talk about the reproducibility of the experiment, right? And so the fact that you whether you talk about simulation or through actual experiments, that if you want to rely on those, it's talking about, can you reproduce those same results? If you give the same set of parameters, the same model configuration, will you be able to produce those results? So that's why I think that your definition of reliability needs to be richer and more expansive, right? And maybe with your advisors, you may wish to just use a different term. So that's the thing that because I just want to clarify that that's what you really mean, right? Scientific integrity and the trust of the data. Okay. So one question and clarification is one of your motivations for trying to provide software support for the scientific models is the notion of time constraints. You're trying to, you say that it's too slow if we're going to just execute the software models. And I guess I'd like to understand better what is the source of the time constraints? Who or what is imposing time pressure for you to be able to get these results quickly?
Okay, maybe I need to describe a little bit a project that was kind of linked to the work I did during my PhD, and really it was part of associating what we call representative or of the government, so mayors, but represented of, for example, regions and different part of the country. Sorry. And what we wanted to do, they wanted, to make decisions about the land use and have different information and basically have kind of aggregated value of the risk according to the scientific part of the hydrology phenomena, but also economical phenomena and so on. And they wanted to interact with the different results and have those results quite quickly, because those people are kind of difficult to gather together in a one meeting. So if we need to, when they have some solution, for example, building a dam or on the land use, and they want to have the result and see the different impacts quite, interactively. If we need to wait for 2 weeks, even a month, it will, postpone the action that need to be enacted, and sometimes it's quite critical. So that's one motivation of that time constraint, really, about the fact that we need that interactivity. They told us that they needed to interact with the tools and the results.
Okay. So that actually helps quite a bit, right? So it's not just the fact that the models take a long time to execute to get any kind of answers. It's the fact that they want to have a dynamic and much more interactive inquisition of the models, right? And so I guess maybe that would be worth to explicitly state, because I think that that's actually quite different than just saying, oh, I have a time constraint. Because time constraint says, well, I have a day or I have a week. But that doesn't sound like that's the impetus, right? The impetus was the fact that they wanted to be able to interactively pose queries and then be able to use that as the result of having a dialogue, right, with the models and stuff, right?
Exactly.
So it's the push to have a dynamic, a very interactive session with the models or interaction with the models. So I think that's worth clarifying, because I think that actually is a huge motivation for having this capability, right? Is that interactive notion. So rather than sort of black box, push a button, and then come back to the results, right? You wanted to pose a query, get a result, pose another query based on the previous result, right? So there's a whole process there, right? But they want to be an interactive process. Okay. So thank you for clarifying that. So that's something I think is worth clarifying explicitly.
Definitely. Yeah, you agree. I agree.
Okay. I think the other question I have is, you also mentioned that there's this trade-off approach to exploring new scenarios. And I guess I wanted to get a better understanding of what kinds of trade-offs, right? And also part of this is that you were moving towards a more optimal trade-off. So whenever we use the term optimal, we always want to know, what are your metrics for measuring optimization, right? So first question is, what are the trade-offs? And then in order to get an optimal trade-off, what are the metrics that you're using to measure those trade-offs to determine whether it's optimal or not?
Okay, so the trade-off is globally reducing some accuracy of our results to gain some performance, but here it's really execution time. And why we do that trade-off in our case is because when we use the scientific software in a context of decision making, decision makers don't really want to have information such as, well, the underground water has changed from 1 millimeter every day and so on. They don't need those scale of details for their information. So we can relax or kind of reduce a little bit the accuracy of the results produced by the former scientific software to gain that execution speed. And regarding the metric, well, we did use a metric that was given and elaborated thanks to the expert domain. And the metric that we use is that if there is a difference in accuracy of less than 0.1 meter, so 10 centimeters along the whole simulation, it's okay because it's not that dangerous. And especially, well, I won't get into the details, but if the data table is in not really in that, according to where the data table is in the soil. So if it's close to the surface, we don't want much discrepancy. And if it's deeper, that's okay. So we put that into our metric. We did think a lot about it, and we talked with experts. But I understand that maybe what we could also think about is maybe using a metric that could be given also by the decision makers, maybe how much information they want about the risks. Is that another metric they want, another scale that they can think of much, more easily, sorry. So yeah, that's also something we did think, I did think about, but it's difficult to have meetings with those people, and we did ask them about that, and sometimes they don't really know how to measure that, because it's really new to use the scientific software in that context. So they haven't really thought about it. So there's also some work to do about it in the metrics, but yeah.
So actually that's very helpful. It sounds like, though, that depending on the stakeholder, right, You could talk about policy analysts, you could talk about policy makers, you could talk about the individual scientists, right? And you could even talk about, I know that Professor Komamal has worked with farmers, right? They're looking at how to do watering, for example. And so then you have a different stakeholder. So it seems that depending on who your stakeholder is, will dictate which trade-offs you're going to make, right? Because if you're a policy analyst, perhaps you're more interested in the economic data or the economic models, and maybe some aspect of the environment. But if you were the farmer, you're probably very interested in the environment and also the impact on crop productivity, for example, right? And similarly, the optimality metrics will also be dependent upon your stakeholder, right? So the trade-offs themselves, how you decide which data, which aspect of the model to abstract, I would use the term abstract, right? And then also, you may even decide how to determine the granularity of the data, right? I mean, how frequently are you monitoring how frequently are you actually polling the data itself? So that, and also going towards your notion of one of your contributions is the generalization of this framework, right? Is that you are saying there's not one size fits all. Depending on the domain expert and your stakeholder will determine which dimension you're going to do for the trade-offs, right? And also which metrics you're going to use for measuring whether those trade-offs are indeed optimal.
Yeah.
Right? So I think that that's perhaps worth mentioning, that your approach, your framework would support that generalization, right? In terms of making trade-offs in the first place, right? And then also being able to customize the metric for those different types of trade-offs depending upon the stakeholders. And it sounds like it is going to be dictated by your domain experts, which would be directly related to your stakeholders of interest, right? Because for each one of your stakeholders, you're going to have a different kind of domain expert, right? I mean, you have an economic expert, you might have a farming expert, you might have a hydrology expert. They will each help you to pick and choose different trade-off analysis criteria, right? So go ahead.
No, I just wanted, that's absolutely right. And the motivating example that we used to do that approximation technique and so on was to provide a way to make the execution time faster, but also for the model to be used for decision makers, scientists, but also the general public. So what you're saying about using different metrics, using different ways or to extract or approximate according to that stakeholders, if I can say. So that's perfectly right. And also the fact, maybe I didn't really highlight that, but the fact that because the metric is provided by the scientist or the domain expert here, it's just a kind of value. So with a software engineering point of view, depending on the case, we can just take another metric. So quite easily with the implementation. So that's great.
Yeah, it's actually quite powerful that way, right? So my last question is perhaps an observation and maybe related to what I was just saying. So the motive framework that you mentioned, I think that you're considering that to be your first contribution. Is that correct?
Yes.
So I have to say that I'm a little bit, I guess I'm not sure if I say the word confused. So as being one of the members of that collaborative group, it was a very exciting time, and I think that we really benefited from having a truly multidisciplinary effort there, and I think your contributions, your input was actually quite valuable. So I guess my concern or the issue I want to pose is I think it's difficult to assess. I mean, it was a group effort. It was a very intensive effort, and I think that we had a lot of fun, and I think we actually put together a very important piece of work. But I guess I'm not quite sure I understand, and maybe I just don't understand the different systems, but the way it's phrased, and I know you totally attributed the fact that this work was a result of this group collaboration. Mm-hmm. But I guess I'm trying to understand how do you identify your specific contribution to that work and making that as one of your key contributions for your dissertation? I don't know if you're just taking the framework as a whole and calling it one of your contributions, or is there a specific dimension or a specific aspect of that framework that you have customized, maybe along what we just said, right? Maybe the motor framework was sort of an inspiration, but then you are specifically looking at, you know, different aspects of that motor framework. For example, looking at how you can do trade-off analysis, support trade-off analysis explicitly according to domain experts, and then allowing you to customize the metrics to support the optimal trade-off analysis. I just want to know, you know, what is your perspective as to, in the context of the motor framework, what is your contribution, you know, that is something that you could say is all yours because it's part of your dissertation, mm-hmm. right?
No, it's not the global framework. It's more the fact that I use that framework to understand and to formalize what the different, well, how to apply or the different approaches. For example, what I can say is more my contribution is making some instances of that framework. One for example, more the decision-making part of how to use scientific software, but also for the trade-off optimization, for example, how to use that part, and the different instances, and trying to put those two instances of the loop aggregation technique and the trade-off optimization technique together to answer the context of that decision-making process or context, which is really kind of a socio-technical system also. So it's more, a contribution is one implementation, if I can say, or one big instances of the scientific model I use for decision-making and applying those techniques, specific techniques.
Okay. That's great. I'm so glad that you said that, right? I think that, and I think that the rest of your work would actually support that claim. I think that there's perhaps some way to better clarify that that's exactly what you're doing, right? Because I think the way I read it, it's almost like you know, the motor framework was included there. But I think that you're exactly right, and that is indeed a contribution, right? You can somebody can take a general reference model, right? And it's a conceptual notion, it's a conceptual framework. Mm-hmm. But if you can actually instantiate it, right, and then actually customize it to support still a fairly general class of problems, that indeed is a contribution, right? And I think that putting it that way, phrasing it that way, you know, I think is actually quite important. Because I think that is valuable to the community, because otherwise the framework itself is abstract, right? It's really just it's almost like a reference model, right? But the fact that you can take that and customize it, you know, to apply to scientific modeling, right, for decision-making purposes and for exploration purposes, and then you also took it one more level of instantiation and actually applied it to a real system, right? I mean, that's one more level of contribution. But I think it is important to clarify that you took that general framework and then you specialized it, you customized, instantiated it to apply to scientific modeling, you know, and to be able to integrate the different models and also the parameterization and support the trade-off analysis, right, for doing the what-if explorations, and to be able to then support the trade-off analysis with the data. I think that's actually quite important. So I would strongly encourage you to make that clarification in that chapter to really clarify that is your contribution, right? Because I don't think that you wanted to get confused that the MODA framework is your contribution, because that was a joint effort. But in fact that you took it and instantiated it in a very, very
specific,
well-defined way, I think that's actually quite important. Okay. So that's all I have at this point. I think that you did a very good, nice job of clarifying and answering my issues and questions. Thank you.
Thank you very much.
Thank you, Betty. Now I give the mic to the second reviewer, Gordon.
Yeah, Thank you very much for that, and thank you, June, for that excellent and very clear presentation. Just before I ask my questions, I would like to congratulate you on an excellent thesis.
Thank you.
I was delighted to be asked to review it, and I thoroughly enjoyed it. And just a comment as well, it's a very brave thesis topic, given the cross-disciplinary nature of your work. You know, I work in the same cross-disciplinary mix, and it's challenging. So it's a brave thesis and an excellent thesis, so well done.
Thanks.
And I'm just sorry we can't all be there to celebrate the occasion, but perhaps in the near future. So I have a few questions. The first one, I just wanted to pick up on the optimization and the kind of acceptance criteria part. One of the, and this is thinking about that framework over time. If you want to repeat an experiment, or indeed you want to run models more constantly to monitor. One of the most annoying things about the environment is that what's true today may change in the future. In fact, it may change drastically because of extreme events, and you may start to see results that are really odd but actually correct because of extreme behavior or non-linearities in the system. So I wonder, do you think there's a way of extending your approach to optimization that would deal with the temporal dimension and how things change over time? Perhaps bringing in some of Betty's skill sets around, you know, what we know about adaptive techniques.
Yeah, and you mean, for example, when applying the approximating technique? Yeah, so...
Yeah. Well, what's the optimal today might not be optimal tomorrow.
Yeah, of course. And well, of course, it could be nice to also, well, apply that technique and trying to... When applying that technique, we will produce some simulations, some results, and then maybe later on use those results to kind of guide or adapt the application of that loop aggregation techniques. For example, adapting the fact that predictive models need to be tuned continuously to be able to have the best trade-off depending on different cases we use to build that predictive model. So there's that. And I was thinking also of something else. My thoughts are going away. So adapt it to use kind of the continuous improvement of the predictive model. And also, it's not maybe linked to that, but I was thinking, you was saying about specific or extreme events that are really kind of punctual. And I was thinking first, maybe you were talking about the fact that we are iterating and removing some iteration, but maybe we can adapt that value of aggregation, maybe depending on, we know for a simulation, for example, there's some critical moments, so there to have different aggregation, maybe less aggregation or less skipping of computing iterations for some specific part of the simulation. And for example, parts that correspond, for example, in hydrology, when it's summer, there's not really much water entering the system, so that's okay, we can approximate a little bit more. But when it's winter, that's really kind of critical period, so maybe aggregate a little bit less. So we can also think about adaptability during that process, but also for different simulation and scenarios along the time. So, yeah, definitely.
Yeah. Unless you live in England and then it rains all the time.
Yeah, well, I'm not talking about Brittany because I love Brittany. I come from Brittany, and people say it's raining a lot, but no, it's not raining a lot. It's sunny also, so yeah.
Yeah. So another area I wanted to ask about was legacy software and your experiences, because one of the issues here is that you're working with legacy models that are large, complex, and written many years ago. And that must have caused problems with you. So I'm curious how that works two ways. How you retrofit your techniques on top of legacy software. But also, part B to that question, how would you like to see scientific models constructed in the future so that they're easier for you to apply such techniques?
Well, that's a really interesting question. First, I did use some legacy software because the model was, well, in hydrology, it's a kind of standard model, which is ModFlow, and it's written in Fortran and so on. So, that's one thing that motivated our implementation of the black box implementation of the technique. That way, we don't really need to have access to the model. We want to modify it. We take it as it is, saying, okay, it was validated by the community, it's commonly used and so on, widely spread. So we just adapt our use of that software by applying it as a black box implementation. So that's one way. It was quite, a little bit complex to make it run on my personal computer. So that's one experience with legacy software, because sometimes it's not really up to date or adapted. So and you were talking about how I envision scientific software to be developed.
Yeah. Could you do more in the future and maybe get over the black box nature if you had the freedom to
I know there are some
reverse engineer or reconstruct models in the future?
Yeah, hopefully, but we could do that. But also, I know there's some type of framework that try to, when developing the scientific software, to have some formalism, ways of describing, for example, those information are variables that can, change. Those are parameters that won't change. Those are the equation that are, the function deals with the computation of the equation and so on. So if there are some kind of, framework that kind of everyone is using, we would know how to, through an interface or API, know that, okay, that model, we know that we want to modify only the variables and not modify all the things inside the model. That could be nice to do, because it will be kind of automatical and we won't need to be inside the model. And we can also use that type of framework about defining the different elements of the scientific software to make different simulation models, for example, interact together, share information, and so on. I know there's some work that are research in that direction, so that could be a nice thing. And also, open source software should be nice also to be able to check, and of course about, for example, the validation process. The fact that people are using legacy software or software somewhere and trying just to calibrate the software, we would need to have some, to be able to look inside the software to be sure that, that software we are using are being validated through software engineering concerns, but also the scientific part that is important. So,
Thanks for that. I just wanted to again pick up on something Betty touched on, and that's the relationship with different stakeholders and also the modelling community itself. I'm curious, how did you find explaining what you're doing in terms of approximate computing to these different communities? Did you have difficulties? Your modelers could be quite precious, for example, about their models, they really own them. And also the end stakeholders as well. There's another dimension to the question there.
Well, it was quite a little bit complex at first and then interesting when the discussion was starting and so on. First, maybe I will take an example. I was discussing with hydrologists and presenting my work of saying, okay, in some examples you can approximate or only run your simulation one iteration out of 10,000. So in fact, it represents one computation every 10 years, or approximately. And for them, because they are really kind of, they want to represent the behavior of the phenomena really accurately, precisely. So they were shocked because like, what? So the model, I put so much energy and want so much data and so on. It can be resumed as only one computation for during 10 years, even if some phenomena are kind of crucial, for example, during winters and so on. So 10 years were quite, a lot for them. But first they were shocked, and then they say, okay, maybe from that information about how much we can approximate our model, we can maybe understand a few things about the physical phenomena happening there. That maybe the model, the variables we use to represent those phenomena are not really maybe specific enough, or those variables, physics variables that represent different phenomena, are not really important in what we observe, or something like that. So it was also a way for them to extract information for their domain. So it was really nice. And explaining that to, for example, decision makers and so on, well, it was much more difficult. It was, I did an initiative. It was kind of explaining my thesis in 3 minutes, and I used different examples that were really kind of down to earth to try to explain it, because it was quite difficult to explain it. But that's okay, I think.
Yeah. So I think one final question for me, before I hand over the floor. You meant this is about your future perspectives, and you talked about pulling in domain knowledge. And it's probably an unfair question because this is work you've not done. But do you have any thoughts about how to do that? How to include domain knowledge into your frameworks going forward?
If you're talking about, for example, the trade-off optimization, we were more, we can focus that information, especially on the different, the definition of the features that can, giving more information about each cases and differentiate between cases. First, we try to do some features about the geomorphy of the geographical sites. We use different information, for example, about the weather, about the presence and how much water there was on the sites and so on. So we try to do different domain-specific features, and some of them work better than others. So there's something we did. We didn't go much, far, because we didn't have much time also to do that. But there was the beginning of an investigation on what type of information about the domain can be integrated and how much it can impact the quality of that prediction. So in that way, in the feature selection information, of course, about the different trade-off about the quality and how to measure and to understand what can be done. And at the moment I'm not really thinking about different things about precise methods I've used and approaches. But there's definitely improvement about integrating more knowledge about the domain.
Yeah, I think that's a very rich area for future study. So I could go on forever, but I shall constrain myself, and I'll hand over the floor to someone else.
Thank you.
Thank you very much, Gordon. Now I'm going to give the mic to Serge.
Thank you. Can you hear me?
Yeah.
Yes,
perfectly.
Yeah, thank you Jean-Michel for giving me the floor. Bonjour, June. So good morning and afternoon to everyone. Greetings from Macau in the Far East Asia. So thank you for this very clear presentation that really complements what is inside the manuscript. And I would also like to thank the supervisor of your PhD thesis for this invitation to be part of this jury, and also for the opportunity to share my views and my questions about your work. So I will try to keep my intervention quite short because this is already late in Macau. It's almost 11 p.m. right now, and my brain already starts to slow down a little bit. So I will try to keep my intervention quite short. I would like to pinpoint some aspects of your work that I really like because they are very close to my research interest in the human system. So very briefly, some details about my background because you will see that we share lots of common interests, but maybe with a different perspective. So I'm a computer scientist working at the intersection of software engineering, AI, and complex system modeling. So I'm currently the head of research at United Nations University Institute in Macau, and since March 2020. And I was previously working at IRD, it's a French research institute on sustainable development. And I was working in different countries like Vietnam and later in Central Africa and Cameroon, working on various modeling applications. I was applying modeling to epidemiology, disaster risk prediction, agroforestry, and many other applications. So since I'm working at the head of this UN research lab in Macau, I'm more and more also interested in policy and the relationship between policymaking and decision-making tools. And I will come back to that later in some of my questions. So I remember that we first met was maybe 3 years ago, something like that, at the Bellows workshop, and we have been worked together to with some other people. Something like that. At the time that we were able to travel. So, very long time ago. So we are involved in some people inside the jury together, and one of the outcomes is worked on by this modern framework that you described in the chapter 4 of your PhD. And happy to see you now at the end of this PhD journey and to discover that you have done quite incredible work in this workshop. So, first of all, and it was already mentioned by Gordon, really like the cross-disciplinary work, nature of the work, ranging from software engineering to environmental science modeling. So it's quite impressive, this range. And I know that this is already something difficult for senior researchers like me, and I can imagine that. Well, for you, especially during the short duration of a PhD, it's quite difficult to do that. So really want to congratulate for that. After reading the manuscript, I see lots of things that resonate for me, especially the question regarding the use of modeling tools in order to solve complex systems like climate change. And more generally, everything related to that give us an understanding of how the modeling tools can help us to achieve the SDGs, so the Sustainable Development Goals, because I'm working at the UN, so this is my core interest, the SDGs, so this is something that, very close to my heart. So when I say complex system, in fact, I'm thinking not only about the interplay of these different fields and disciplines, and that you need the expertise of different experts, but also that when you are working on models, and maybe this is something that most of the people forget about, is that you have to also deal with the negative and the positive impact of these models on the policies and more generally on everyone's life at the end, because these models will serve to design these policies. And this is very important. And I think you mentioned that at some point, that to have not only the scientific perspective, but also to put this in a more social-technical, environmental system perspective. This is quite important. Because at the end, everything is tangled, everything is intermixed, especially when you are dealing with the UN SDG framework. And most of the people, they are considered them as silos, and they are not working on the relationship between these different goals. And working in the UN, I really like that you mentioned at the end the sustainability, because I think it was in one of your perspective slides, so I really like that. And that you also mentioned that we need a more holistic view. This is something I also share with you. Something I also like that you mentioned the fact that we are living in COVID-19 time and the role of model in that context, because these models will be used to design policies suitable for all the citizens. So this is, even if you don't work directly on that specific topic, I think this is very nice to mention that. So let's move now to my questions. We try to frame them around my interest about models and policy making. So I have two questions. maybe quite different from the previous questions because I'm working in the UN system. So I want to start with your contribution about the approximate computing in chapter 5. Just on a side note, I'm a bit surprised that you didn't mention the work of, in the state of the art, there's the work of Shlomo Zilberstein, I don't know if you know, but that has done a lot of work on anytime algorithm, and I think this is quite similar to approximate computing, so I didn't see this work mentioned, so we can add it later.
Okay.
So basically, it's quite similar. It's an anytime algorithm, that algorithm that you can ask any time the result of the answer, and if you wait a long period of time, you will have a better answer. So it's
okay.
maybe something that we can add.
Okay.
So coming back to my question, I want to ask you a question about explainability of models, because this is something important issue, especially when you have to deal with the recommendation of policies. And so an important issue for policymakers or for stakeholders that they should be able to have ways to explain the result of the model simulation.
Yes.
This is what you already mentioned, that is related to the black box effect, in fact. And so it's very important when you have to deal with decisions and consequences of this model on the life of the citizen, that this is very important to have more accountable models. And in the chapter 5, you introduce this idea of approximate scientific computing. And I think it is really interesting in the idea because it allows more interactivity with the stakeholders. Mm-hmm. And at the same time, you try to keep the accuracy of the model. But I'm a little bit concerned about it might be difficult to explain, to understand the result of this model to both by the scientists and the policymakers. For example, you know that, for example, in the case of some surrogate model, when you are using machine learning approaches, sometimes it's, because you are using machine learning approach, this is a problem. And I'm not sure this is a problem in your case. So is there any explainability impact related to this idea of approximate computing? This is my first question.
I don't think so, because, well, they would have used the same model, initial model, that is not approximated, so it produces the same kind of results. So, for example, here, the level of the underground water. So using, trying to explain those results to stakeholders, to decision makers, for example, it would require the same effort and energy to explain the result of that first scientific software and the approximated ones. So there's not really a difference in how the result will be explained, but what we can maybe integrate into the metric that will be used and understandable by the decision makers, integrate the loss of maybe accuracy or the fact that we may have more or less confidence in those results. But because decision makers, as I said, they won't look at the raw results of a scientific software, but more an aggregation about the percentage of risk of flooding, for example, over all the different scenarios. So another metric will be, elaborated to integrate those different specific results. So I don't really think there's really a problem of explainability that is different to the initial scientific model. I don't know if it's answer quite what you were explaining or trying to ask.
Yeah, I think it's something that I'm not really an expert of this kind of approaches, but this is my concern as someone who is interested by policy making, and I know the difficulty of using these kind of models with policymakers. So because
some effort will still be needed. Well, we need to make some effort to then explain the different results of those simulation models. There's also some work that needs to be done for them to directly use the model. At the moment, it's not that efficient for them to understand that, so some work needs to be done on the metric, or they need to understand and manipulate really.
Okay, so I have another question about that is maybe much broader, and that is close to the previous question from Gordon.
Okay.
So I read in your document in the intro, I think that you met several stakeholders and policymakers from various fields, governmental, representative at different levels, national, regional, etc., representative of several environmental agencies. So one of the main problems that we have in this context that these people are not used to this kind of evidence-based decision-making tools, and like the one that you described in your work. So I'm always thinking about how to raise the awareness of policymakers about modeling tools, and I guess that after discussing and meeting all these policymakers, you have come up with some ideas on how we can convince them about the relevance of scientific modeling tools in the context of decision making. So do you have any thoughts of that?
Well, I was maybe quite lucky because the decision makers I met were already kind of convinced of the use of those modeling tools or using software, scientific software, to as a to support their decision making, because they are sometimes faced with questions about the population, about citizens that they don't really know how to answer because they have kind of no information. So they need to make decision and to be responsible for those decisions. So having some kind of information to help them, to guide them, make an efficient or sustainable decision, or I would say rely on, but to use that as some proof or evidence that their decision is kind of logical. So they were quite already, convinced of using those scientific software to help.
Okay, so they changed their mind. Maybe there was some resistance at the beginning, and after a while,
and we also made
change of mindset.
Yeah, and we work well. I did that doctorate and PhD, but also with a collaboration with a PhD in hydrology who really developed the model I was using, Alexandre, and together we kind of come up with a mock-up of what the tool could be used, the interactive tool will be in the future for decision maker to use. We did kind of a mock-ups or a fictive way, but they could interact with false results and a simple simulation. So they had a vision, they could see what the tool would be, and they were quite happy with that, and we were kind of, asking questions about if they could do that, and so on and so on. So there was kind of a really interactive brainstorming, and they were quite passionate about it. So I was lucky, I think.
Okay, thank you. I said at the beginning I will not ask too much questions, but we'll stop here. And I just want to say that we'll soon have a new position, junior position in our institute, so the main institute. So if you are interested, you can apply, because we are looking for people like you to work on modeling and policy making.
Okay, that's a good
So
information.
thank you for your answers. So great work. Lots of contribution, great manuscript, very well written. Thank you very much.
Thank you.
Over to you, Jean-Michel.
Yep, thank you, Serge. You stay with us, right? You don't...
Yeah, sure, I stay with you. I will not sleep immediately, no.
Okay. And Ceci, you want to follow up?
So I'd like to join my colleagues on saying that it was a really nice manuscript and a great presentation. It was really nice and pedagogical, so I really enjoyed it.
Thank you.
I'm not a software engineer expert, nor environmental science expert, so I will ask more general questions. But I have many of them, so I will start also. So the first question I was thinking of, it was about the models that you are using for hydrology part. And in fact, at the beginning of your manuscript,
Yes.
you're citing IPCC, the Intergovernmental Climate Change, Panel on Climate Change. And what they are using, usually it's not a unique model. They are mixing models. And I was thinking, in your context of approximate scientific there's an easy way to suppress the models, but I guess that's not the easiest one.
Yeah, okay, so I'm just going to repeat because I don't know if the mic is working great, but how to apply, then your question is how to apply the approximate computing techniques, the loop aggregation, but not only on one specific scientific software model, but on several scientific models interacting together and have kind of a system of different models. I think it will also be linked to the global metric of acceptability we could use on the global result, because at the end what we are interested in is the global result of all those simulations. So we would need a kind of global metric, and from that trying to maybe different rules saying maybe those phenomena are more important or are impacting the results with higher magnitude. So maybe putting those aggregation or approximation of that model maybe a little bit less and more on another model, and trying to know how they interact and to represent that interaction, and also how the accuracy between different models are transferred. So that's really complex, but that's, I think, linked to one of the perspective of what I was trying to say, is because I've worked at a quite simple level, but it's quite complex, but still simple level. Now we need also to think of how to apply those software engineering techniques on complex and systems. We are used in software engineering to deal with complex systems, but not really when it's scientific software that are interacting together. So I don't really have a solution now, but I know that it will be even more interesting to look at. So yeah, definitely.
Thank you. Also, I have a technical question. Maybe I didn't got it right. So when you spoke about interpolating,
Yes.
I guess that you afterwards, I think it was just this slide, you were telling it's in fact a linear regression.
Yes, I'm using.
So I was wondering, why is it a linear regression, and did you try other interpolation methods or not?
Okay, with my example, I did try several aggregation methods, and I only tried the linear regression approaches. We thought about using different ones, but because of time and so on, we did not explore that. But also, that's also interesting to know, because we can also think of adapting the interpolation function to also, how I say, maybe represent, for example, if we are in winter and so on, try to adapt that and maybe to have a finer interpolation, because it's quite automatical here and not really we haven't used some domain knowledge in that interpolation, just a mathematical interpolation, simple one, because we wanted to prove that it was possible first, but also, we can explore different ones.
And I have a similar question on the way you are treating the data. So the approximation method, that's this slide also.
Yeah.
This one.
Yeah.
So you are taking one line over two.
Yeah.
Which is a kind of a compression technique, let's say. And in fact,
Yes.
in data analysis, there's a lot of compression techniques for videos, for instance, and so on, which are less naive ones.
Yeah.
Could you apply some of them, or did you look at it, or not at all?
Actually, I think those compression methods are kind of also part of the approximate computing big thing, because usually approximate computing is used, for example, on video and so on, for example, in Netflix, depending on the quality of the connection you have, for example, and so on. And so here, what you're saying is having more complex way to aggregate them.
Exactly.
Yeah, and again, it's also a way to integrate, the domain knowledge there, because the way, for example, when it's a video or a picture and so on, it's really what I was saying at the beginning, it's the interpolation operator is domain specific. And here we have just again use some simple ones. So we did say a mean. We just did duplicating the value and so on. We explored different methods, but we can also have better way to do that. But it was a first, I'll say, a proof of concepts, you know, to prove that it's possible, and then we can also optimize it.
And a similar question as well, it was on the learning algorithm, so
Yes.
I see that you use the random forest regression
Yes.
algorithm, and I was wondering how you know which one to use.
Okay, so first, because one of the point is in the literature is quite the most used one, but also because we don't have much data, we couldn't really use other ones. I tried, for example, gradient boosted trees, and decision trees, simple ones, but the results were not as good as random forests. So I only described that, but yeah, but we can also think of different things. But it was also again a little bit to prove that it was possible, and again, yeah.
On a different topic, so we
Yeah.
spoke on the first questions about reproducibility,
Mm-hmm.
and I was wondering whether the code is available, maybe more future version would be used by other people in the team.
Okay, but that's great. That's also something we were discussing because, well, I was mainly part of the software engineering team, but also I had weekly meetings and different meetings with the team in hydrology, and we did exchange, and they have started a project of putting all the code they have and how they use the different models and so on in a unique repository on GitLab, open source, together. Well, first you have the same use of the code, and for example, to share some functions that were developed to other people to help them and so on. And by integrating all the different work together, my personal code is not available yet because it was dealing with a model that was not published yet. Alexandre was doing it, but it's in progress, and I want to integrate my part of loop aggregation into their framework or their how they use the code about manipulating their models, analyzing the data from the model, and so on. So it's in progress, and that's really the idea of doing that, and for them to use that and to be able to explore their model and so on. So, yeah.
So I have a last question, which is a bit higher level
Okay.
question, maybe a bit more difficult also.
Let's do it.
So I know that you like teaching,
Yes.
and so you said it, and all the other speakers or the other reviewers, they said it as well. It's really difficult to handle such an interdisciplinary subject because you need to master both
Yes. Yes.
topics.
Yes.
And so during the teaching, especially in France, we don't have such lectures, let's say, which are interdisciplinary.
Mm-hmm.
And I was wondering whether you could see the work you did in your thesis, which is in between, let's say,
Mm-hmm.
but more on the software engineering part, as a concrete example that could be teachable
Mm-hmm.
to students either in hydrology or in computer science to give concrete lectures in fact, which is the point that is missing in France about interdisciplinary topics in which you would solve about this.
Well, yes. It's idle. I want to teach them and to speak about it to students, especially because even in research, in papers, and people are definitely aware of the fact that multidisciplinary, transdisciplinary is necessary. But in practice, it's more difficult. For example, finding funds, how to evaluate the work, because it's two disciplines, so which journal, which conference, and so on. So yeah, it's really even complex. The subject is complex, but dealing with it is also complex. So, and about teaching, well, I did teach and prepare the different courses for scientific modeling course, more in the software engineering master degree and so on. And I think maybe that type of work could be used, maybe a motivating example to, explain how it is important to think about how the software is used and how scientific software are kind of special and so on. So, yeah, I think there's not those type of class much, but I think there's work that is, improving and more integrating that influence and the fact that, well, we are producing software, but we need to be aware of the user, how the software will be used, and the potentiality of impacting our world and sustainability, of course. So, yeah, well, I hope it will, and I do think it is interesting to study. Well, I did a PhD on that, so yeah.
Thank you.
Thanks.
Okay, thank you, Cécile. So I'm going to take the next set of questions, not to avoid the other ones, but most of the time the advisors they like to react to the questions sometimes. So this way they will be able to react to mine. Thank you very much first, and congratulations. It was a very consistent presentation with the document, very clear, very pedagogic, as we say in French. Congratulations also for the English, but I recently heard that you had a good teacher. So, I have lots of questions, of course. I will try to reduce them. I have 3 sets of questions, one about generalization, the second set about P. I have a problem with P. And the third one is about the tooling, something that maybe has been covered by the recent question. So let's start with the generalization. If you remove environmental science from the title of your thesis, what remains? I mean, it seems to me that it is not at all specific to environmental science.
Okay.
Would you agree with that? And if you agree, or if you're not, what is the precise characterization of the simulation system, scientific models you would be able to fit into that?
Okay, so yeah, that's really on point, because, well, the environmental science part of the PhD is really kind of a motivating example, because, well, all the different issues and requirements made us elaborate that specific method. But when we take a step back with that method, because the way it was implemented, it can, well, be say transferred or applied on different type of models that not necessarily are from, for example, studying climate change and so on, but more maybe need some information quite fast and can reduce or trade off some accuracy. For example, I'm thinking of maybe an auto-drivable car that, well, there's something that is unexpected. We want to make a decision about it, so we need to run some complex model quite fast. So we need to have a reaction panel. So yeah, maybe using the loop aggregation technique that can be useful there. So I would say environmental science is more the motivating example, but also the fact that the model we used, because they are scientific, are a little bit different, and we needed to adapt different software engineering technique about it, and also the fact that we did use domain knowledge. Well, it's not necessarily environmental science if we want to apply it, but we need those information. So we need to take into account the fact that it's another domain than software engineering, and environmental science, it's part of this more broadly science field. So we could maybe look at different other models, and about the question of what type of models, I think models that are, well, we need some iteration to be able to skip them, and well, a for loop basically, and I think it's the main requirements, and the fact that we can, well, we need to have an accuracy or metric also linked to that, but basically that's the main requirements about it.
Okay, because I was interested by the decision-making
Okay.
aspect, and there's
Uh-huh.
lots of environments
Yes,
where
yes.
decision-making is needed, right? So let's take a concrete example, a selfish example. Let's say Airbus
Okay.
wants to make a
Yes.
decision about
Yes.
something, changing the type of engine they
Okay.
use. Would they fit here? Maybe the answer is no, because maybe they don't need a very fast answer, and maybe because they don't have these scientific iterative models. Would I
Okay. Actually,
answer correctly?
that's quite funny, because I was discussing with someone working not at Airbus but at Thales this weekend, and I was explaining my research, and he was like, "Oh, I will need to read your thesis manuscript because it's really interesting." He's in charge of the mathematical aspect of the autopiloting thing, and he's really using the the idea that we don't need to have a lot of data to have kind of the answer of what to do, because it's critical, so sometimes we just don't need to have all the information. So I was interested in that type of work. So, well, sorry, your question about Airbus, yes, I think it can apply on that, trying to, instead of iteration, maybe tasks, in a way, so less important one, not to compute them.
Okay. Thank you. Yeah, it was in the generalization field. It was the question about the time. I had the same question as Betty. You talk about time a lot.
Yes.
You talk about, okay, I gain 96% of the time, but you never give us a scale.
Okay. Okay.
Is it days? Is it month? But I don't wanna answer. I think I got the answer from your answer to Betty, and I also concur that the characteristic is the reactivity, being able to dynamically replay, changing a little bit of parameter here and there. Okay, I got this one taken by Betty. About this P, and I think you also this one you also maybe started to answer. I think it was to Gordon maybe.
Okay.
I was wondering why P is fixed.
Okay. Yeah.
I mean, it makes sense if the data are very linear, right?
Yes.
But what if you mentioned an example? I thought you were going to say that P is different in your example where you have critical zone. So maybe I messed up the two, but to me maybe in the data set maybe you need to be more. But was it the answer you started to?
Yes. Yes. We have applied a kind of systematic aggregation and skipping the same number of iteration, but we can adapt that as an aggregation depending on the seasons or the critical time of the simulation. Yeah, that can be also one way.
So the follow-up question is, it seems that you might be able to calculate P, right? From the initial data set, you're able to try to optimize the value of P, right? Did I get that correctly? For example, you might be able to say, okay, 2 is not a good number. We should use 10.
Yes.
So that means that would you say that you are able to decide about P without the scientific expert? Just based on his initial data? Or is he involved in the choice of P?
At the moment, no, but it's defining the definition of P is linked to the fact that we need to know when the simulation results won't be acceptable.
Oh, okay.
So it's the metric of the domain specific metric. So it is linked. Not directly, but it is linked to that.
He's the one who validates.
Yeah, that's it.
I see. Let's see. Oh yeah. It's a question related to the. I like the term, the scientific integrity. Let's take this this new term that I really like from Betty. Would you be able, or would you foresee a way to provide a confidence value? You know, like the meteorologists, they say tomorrow it's going to rain, and I have 99% or 90% of chance of accuracy.
Yeah.
Would you be able to attach to your decision making a confidence value? Like, I'm really confident, I have doubts, but I need to take a decision.
I think
like that?
I think to do so, we can integrate the loop aggregation change of accuracy thanks to the metric that domains experts have given us.
Yeah.
But we have to understand that, the model I used in hydrology, the confidence is like it's an order of magnitude. They don't have much information. So it's really difficult for them, and that's why it was difficult to build those acceptability metrics, because they are not used to do that. There are so few data from the underground for the information, and that's really specific to the hydrology domain, that they have quite a lot of models, but really few data. So
Yeah, but then it would be even more important to say that. To say okay, I take this decision, but look, I took it from a very
of course. When the decision makers will base their decision on the result, they need to have information about how confident they can be in those results.
Yeah.
But as a software engineer, I can't provide that. There's work to do about the first model we use. They need to have some accuracy metric or confidence, and then we can build on that.
This number is not available.
No, not at the moment.
But if you would impose something like that in an approach, then the combination of those could be
to try to
propagate it.
Yes,
until the
exactly.
final
Yeah.
decision. Okay, makes sense. So the next set of question is about the tooling. I was frustrated not seeing any tooling. I mean, we are in the
software.
the Gemlock house, and I don't see any screen capture. So I was a bit frustrated in this presentation. So could you tell us? Maybe you already answered. So I understood that the code is not available yet because it had not been published, but. Let's say you leave for postdoc or for a position in Asia or elsewhere, and people want to use your work. Will they be able to put their hand into that without you?
Hopefully, that's the goal. At the moment, I was trying to kind of build several type of codes, because there's one that is really specific to the model that are used in the hydrology team, which is a mod flow model in Fortran, but we call them and execute it thanks to Python and a specific library. So I wanted first to integrate my code with those information. So it's a Python code basically, and trying to abstract from that some interface or API for other people to try to implement it and use it quite easily. But that's one of some project I want to do, because that's basically my goal. I'm supporting the fact that we want to have exchanges or discussion between two communities, so I need to provide also the thing. So that's really something that's close to my heart. So yeah.
Okay, good to know. good to know. It seems to me that you've nicely provided references, papers that you published on lots of your part. It seems to me that the fourth part, the one, and I'm surprised, because that's to me that's very interesting, the way you optimize things. And so was it because it's very late work and it has not yet been published, or was it because it's difficult to publish?
I don't know really about the second part, but it's more about the fact that it was at the end of the PhD work, and I had to write that manuscript. And also we wanted also to publish, because we published in more software engineering venues. We also wanted that paper to try to summarize the loop aggregation technique with the learning process and optimization into a more paper towards the hydrology community. And to make also again exchanges and discussions. So it's what we want to do, and I have to finish that paper to submit. So yeah, it's also in the work.
Okay, and that will be my last question. Can you go back to slide 18?
Yes.
It's like 18.
Yes. That's okay.
Yeah. So that's your That's your roadmap, maybe
Yeah.
not the initial one, but I guess the final one.
Yes.
But that's a lot, right?
Yes.
That's how you did it.
Mm-hmm.
If you would have to do it again, or if you would have to define a new PhD to follow up these things, what would you change into that roadmap, or would you change anything?
I think because the two first contributions are more background or knowledge you need to have. Now that they are made, we wouldn't need to look at that, so we understand more about the scientific software and so on. What I would need is more for follow-up research, because there are the different techniques and specific to that context. What are the different contributions that would need to be, elevated or more adapted to the new context of the PhD, the following research? So and more about the different question about how to adapt loop aggregation to the multiple models, having simulation at the same time. That would be really interesting.
Yeah.
Lots of work should be done there. So maybe looking at the first contribution about how different models interact together when they are co-simulation and how they work, and then when we understand how it's done, maybe how to apply that technique on that field. It could be maybe the roadmap.
Thank you very much.
Thanks.
Benoit, you want to start the co-advisors run?
Thank you very much, Michel. So of course I will not have direct question to you because I was part of the supervision. Even if I should have mentioned that I was on the second line. I mean, the first line was really Johan and Jean-Renan that was really doing this very nice supervision. But I really wanted to thank you for this presentation today, and also for having me the opportunity to work with you during these 3 years. And it was really very exciting and very interesting to work with you and on the topic that we addressed. So it's very good. And I also wanted to mention that of course, first of all, a very important milestone for you today. Of course, because it's the end of your PhD. But in the meantime, you're also offering us a very important milestone for us, because it's the first PhD that we see the difference today from the collaboration in between Jean-Renan and us, so in between environmental sciences and software engineering. And if I would have dreamed about something at the beginning when we started to discuss with Jean-Renan, I'm not sure that I would have even think about everything that you did. So I'm very, very happy for this, and I really thank you for all the stuff that you did. And you was really very quickly an important person in the team. You was very involved in the life of the team, and you have driven this collaboration in between the two fields very nicely, in a very nicely way. So I was really impressed by this, and thank you very much for this. In the meantime, I also discovered a very smart, passionate, and hard-working person, which combined both very technical skill, because you did a PhD in software engineering, and you had to implement a lot of stuff and to experiment a lot of stuff, and you did everything. And you also have very nice soft skills that are also very, very important in our work. So combining these two kind of skills is not really common. So I'm really glad to see this, and I'm sure you will have a very nice career in the future. So thank you very much for this. That was really important for us. So it's important for you, but thanks also for us. Yes, that's important for us. I also wanted to thank the jury member. So thank you very, very much, Betty and Gordon, for reviewing this manuscript, and also for all the comments that you made today. And I think that's one of the first PhD defense that I took so many notes, because all your comments was really very, very valuable. So thank you very much for this. And I'm sure we have a lot of discussion to have as soon as we can meet in person, hopefully very quickly. So thank you very much for using this. And also thank you very much to Serge and Cecile for being in the jury and for attending today and asking the questions and all your comments. There was also very good comments, and thank you very much for this. And of course to Jean-Michel for being the president of this committee today, so driving this defense and also for your questions. So thank you very much for this. And of course, last but not least, thank you very much, Jean-Reinald, and thank you very much, Johan. It was a very exciting time working on this PhD, so thank you for the very nice supervision. Thank you again.
Thanks.
And all the best for the future.
Thank you, Benoît. Jean-Reinald, you want to continue?
Thank you, Jean-Michel. It was a pleasure to work with you, June. You know it. I say it for myself and also for the colleagues you have been working with in our laboratory, especially Alexandre. Alexandre is someone existing. He's a PhD student, soon completing his PhD. Alexandre Goulon, I think he's online. And you have lots of quality. I will just say one, which is your capacity of crossing boundaries. You know, boundaries nowadays are a bit touchy. But it's important to have good boundaries so we can work each in our countries without invading too much or being tempted to invade the neighboring discipline. And it's very important to have our own disciplines and to cross the boundaries. And it has been a pleasure to work with you on this, because you were able to work with us, to be in our country, to be visiting, but more than visiting. And it was more than knowledge. It was very competences you have in environmental sciences. And we have also the great benefit to have influences, and more than influences, to have the new advances of the other disciplines. Thanks to you, thanks to the colleagues, and thanks also to the world discipline, because we are not taking all, but we are taking what is ready. I would like also to congratulate you because it's not an easy topic. No. Gordon said brave. I don't know between courageous and brave. I would say courageous in French, but perhaps it's more brave in English. I don't know. And it's tough for two reasons. First, it's tough because the environmental process that you have looked at, like hydrogeology, groundwater, we don't know it. We don't know the state. We don't know the evolution a bit. Cannot say we don't know it. I'm not a geologist. I'm supposed to be here, but we know really few about it, and still we are asked to make predictions. So to make predictions on a system we barely know. I don't think it's better with climate, but and it's very tough. And these predictions they are really necessary. Necessary because we don't have any record in the past of what is happening now with climate change. It's a real new world, and a real new world. You need models, not really to say what is going to happen, but to have some references. And so modeling is really necessary. And the difficulty with the sciences where we have huge uncertainties, that's what you said, Jean-Philippe, that what is the reliability, how much uncertainties, it's really uncertain. And not like an engineering system, it's orders of magnitude. So what you have done, and I think it's the real originality and contribution of what you have done, is not to not that the prediction is something by itself that is giving all what is going to happen. I think most of what is going to happen we don't know, and we cannot say it with just one scenario, just a prediction. And we did a system that is adaptable and that could be adaptable in the future to deal with this uncertainty. And we will have to deal with this uncertainty. It will not change. It will not be removed. It will not decrease the uncertainty. It will probably still increase. And I think that modeling, as you are doing it, it's exactly what we need to tame uncertainties.
Mm-hmm.
We will not remove it, we need to tame it, and I think that taming uncertainty is what we should go on doing in the next few years, perhaps decades. And I'm very happy if you are going on this topic, and if the competencies you have gained, you have used in your PhD, you can go on using it, and others may benefit it a lot. Thank you, Dr.
Okay. Thank you, Jean-Marc. And the last word to the director.
Thank you, Jean-Michel. Thank you, everybody, for being here in the jury today, and for reviewing the work and asking these very interesting questions. I join Benoit to thank you about everything, but I'm really, really proud to be here today, sitting on this chair. It's a big milestone for you, obviously, but as mentioned by Benoit, it's also a big milestone for the team, I think, because this is the first PhD in this domain, and as some of us know, being the first PhD in a team going on one new domain is a bit tricky, and it's hard work, so we really, really appreciate that you've been accepting this challenge. And it's also a big milestone for me, because you're my first PhD as a director, so I'm really happy to be here. And I'm really, really proud about the work we've been doing together. I was really happy to work with you. I remember when we get the funding some years ago, like 4 years ago, and we had to look for a PhD student for this thesis, and we were wondering who we could find to do these challenges. And we were really, really, really happy to have you, because it was really challenging to find someone with both skills, software engineering and, let's say, the field of science in general, and environmental science in particular in this domain. So we were really happy. And I also want to mention the fact that we were probably already mentioned by Bernard, that you were also very involved in the team life. So it's not only about the scientific skills and the soft skills, but also you take fully part of the team life and animation of the team, the gyroscopy and so on. So we really appreciate this, and we really want to thank you for this. Thank you.
Okay, thank you very much. There's this, I don't know where it comes from, but there's this tradition to ask the audience if someone has a PhD and wants to ask a question. That's the time. No, you are all friends of you. Okay. So thank you very much, June. I guess we stay here for the exam. So thank you for joining us in.
Can you make sure that you stop the YouTube?
Yes, I'm doing.
That would be terrible.